Hello everyone, so this is our analog circuits lab project. What we have made is we have designed and implemented an end-to-end analog signal transmission system using a laser optical link and discrete ADC DAC architecture. So we are not using any ADC and DAC chips. Instead, we are implementing that on breadboard and transmitting bits by bits using laser. So first we are taking analog signal input. We are taking from signal generator. So we are taking a sinusoid input. This is the sample and hold circuit using MOSFET. The input goes into the drain. And the source has a capacitor and the output. Now what on the gate happens is we are taking a trigger on the gate. So for some time the capacitor charges. This is the clock we are using for trigger. It will be on for 10 microsecond and off for 40 microsecond. We are generating it from one original clock using the monostable mode. So now when this clock is on, the capacitor charges, and so it creates a sample, and when it discharges it holds the circuit, so it gives us a staircase output. So this is the sample and hold. This is the original timer of 90% duty cycle, and this is the monostable mode. We are using it to give trigger to gate. So it takes the sample, and this is another monostable timer which will use ahead in the chips. So they all are synchronized, and we are taking sampling frequency 20 kilohertz. So you can see the output of the sample and hold circuit. The yellow one is the input, and you can see the sample and hold circuit has converted the analog signal into a staircase signal. So it has been converted into staircase. Now we will use comparators to convert this staircase into digits, binary. So the output of sample and hold goes to the comparators. We are taking 5 volt peak to peak and used 8 comparators. So level are of 0.625, and it will give 8 bit output. So 8 comparators will give 8 bits. Then we are using encoder to convert that 8 bits into 3 bits. Now we have got 3 bits, and we need to transfer it through piezo, parallel in serial out shift register, because we need to transfer bit one by one. So that is piezo. Now piezo requires 2 clocks. One is the original we have made of 20 kilohertz, and another one we need of 60 kilohertz, because one will take the input in the piezo and one will shift the bits one by one. So this is the mechanism we have used for making the clock. 60 kilohertz we have made from the reset of timer 1. The third will be a little distorted, but what we need is 3 clock rises to shift all bits one by one through the channel. So it works in synchronization, both the clocks, and the same clocks we are using in CPO also at the receiver side. Now we have transferred bits one by one through piezo, and the output of piezo is transferred through laser. This is the laser. Now and this is the photo receiver. So they both can operate at nanosecond, and our circuit is working at microsecond, so there is no problem. Now what happens at the photo receiver side is, it is an analog device. It produces some current. So we have used an op-amp based circuit to convert that current into voltages using negative feedback. So what happens is, when there is no light, the voltage will be 200 millivolts something, and when there is light, the voltage will be approx 2 volts. So after that, since we need bits at the receiver side also, we use comparator at 1 volt level. So this is the comparator. It is operating at 1 volt, and this chip can also operate at nanovolts, so there won't be any delay. So it gives us the output as 5 volt and 0 volt as we need for the reconstruction. So 2 volt and 200 millivolt are converted into 5 and zeros. So the output of comparator goes to CPO, serial in parallel out shift register, and we use the same clock as piezo, 20 kilohertz and 60 kilohertz. The 60 kilohertz clock we use a NOT gate to invert it, because the clock sending and receiving cannot happen at same time, so we need at least some delay. So 60 kilohertz clock is inverted, given to CPO, and now CPO will take bits one by one and then give us 3 bits as a output. now this 3-bit output is given, you can see the 3 wires, it is given to the R-2R ladder network circuit. R-2R ladder network, it is the basic digital to analog converter. It is only a register network. It gives priority to the bits according to their value, like MSB, LSB, and the middle one we have 3 bits, so it gives priority according to that, and it reconstruct the signals. So now I will show you the output. So the yellow one is the input, and the channel 2, you can see the pink one is the output. Now I will connect the laser to show you the reconstruction from R-2R ladder circuit. So we put the laser close to photo receiver. So you can see the approximation staircase of the original sinusoid input we have taken, and we can take any analog signal because there is no restriction on that. So now I will change to, let's say, square, because it will be easy to visualize. So I will press the laser again. Yeah, you can see the output which is reconstructed. It is same as the original, same peak to peak voltage. So this was our project to design and implement end-to-end analog signal transmission using laser optical link, and without using the ADC DSA chip, and completely implementing it on breadboard.